Our second example is going to take a look at one of the functions that we saw in the slideshow. At the time, we used this function and a similar looking function to show that they were not inverses. So one question that might follow from that is, what is the inverse of this function? Well, here's a chance to take a look at that and find out. Now, first, before we do anything, we need to verify that this function is one-to-one, because if it's not, we will need to restrict the domain. So that's our first question. Well, the best way to do that at this point is to consider its graph. Fortunately for us, this is a transformation of one of our basic functions, specifically the rational function. This is, if we choose to interpret it this way, which we will, this is 5 times the rational function 1 over x minus 2. Now, we don't normally choose to write it this way, but I did that so that we could more easily identify what transformation is being caused by that multiplication of 5. Now, fortunately here, we seem to have only vertical transformations. By order of operations, the 1 over x happens first, and that means that the operation of times 5 happens afterward. That makes it a vertical transformation. It is a multiplication by a non-negative value. That makes it a vertical distortion by a factor of 5. After that comes a subtraction of 2. Again, it is after the basic 1 over x operation. So this is a vertical shift down 2 spaces. Now, the original basic rational function. Now, if all we have is vertical transformations, anything that's based on x is completely unaffected. Normally, the rational function would have what's called an asymptote, this imaginary dashed line that sits on top of the y-axis because x is not allowed to be equal to 0. You can't have 0 in the denominator of a fraction. So x cannot be 0, and since that's a quality of x, it is unaffected by vertical transformations. Normally, there would be another asymptote sitting right on top of the x-axis, but the vertical shift of 2 is going to affect that. The 5 will not, because if the y value of this line is 0, multiplication by 5 isn't going to change that. 5 times 0 is still 0. But 0 minus 2 does have an effect. So our horizontal asymptote is going to relocate down 2. Now, aside from that, the normal function occupies the lower left and the upper right quadrants of this grid as it's been separated by its asymptotes. Now, the 5 is simply going to make it taller. It's a vertical distortion by a factor of 5. The important thing here isn't exactly the coordinates of all the points, it's more getting a feel for the graph. And the fact of the matter is that a vertical distortion might make it steeper but it's not going to change the fact that it is still in these 2 quadrants. And that is clearly 1-to-1. Any horizontal line can intersect the top right portion if it's above the asymptote, or it can intersect the bottom left portion if it's below the asymptote. So yes, this function is 1-to-1. Now again, it might be worth noting here, since we happen to have the graph and the function in front of us, might be worth noting what its domain and range are, so we can compare them to the domain and range of the inverse function when we find it. So as we said, the domain here, which we could see from the function itself and now from the graph, is that x cannot be 0. So the domain is from negative infinity to 0, and 0 to positive infinity. The range is similar, but because of that vertical shift down 2, it's y equals negative 2 that we will never actually achieve. So negative infinity to negative 2, and negative 2 to positive infinity. So again, good idea just to have those kind of in the back of our mind as we go about finding the inverse function. So we verified that the function is 1-to-1, and that means it does have an inverse. So we're going to start by writing y instead of f of x. And we're going to solve now for x in terms of y. Fortunately, we kind of already addressed the order of operations up here in figuring out the transformations. So if we're solving, we're going to work them backwards. We'll start by adding 2. Since that's the last operation that occurred in the function, it's the first one to be undone. So we have y plus 2 is equal to 5 over x. Now, one way or another, at some point we're going to have to deal with that x being in the denominator. If we choose to think of it like this, with the 5 as a separate piece, we can deal with the 5 and then go about dealing with the reciprocation. So I'm going to take that approach here. If we divide by 5 on each side, that will take care of that multiplication by 5. But it still leaves the x in the denominator, and be very careful of that. The x is still in the denominator. Now, the easiest way to get the x into the top is to simply flip this fraction. Can we do that? Well, not normally. We can't just flip a fraction out of nowhere, but because it's equal to another fraction, if they are equal in value, then their reciprocals must also be equal in value. So as long as I flip the left side as well, I'm home free. So, as in the previous example, and as we will always do at this point, now that we have solved for the output variable of the inverse function, we're going to flip-flop those and use function notation. So 5 over x plus 2 is equal to, well, when we use function notation, we don't usually use the variable for the output. We usually use something like this. So this is our inverse function. Now if you do go back into the slideshow and look at this slide, this was on slide number 9, you'll notice this is actually exactly the reciprocal of the function I gave there. So it's got the right elements, and it even looked that way at the time. But if you'll notice, when we composed the functions in the slideshow, we didn't get x. We got 1 over x. We got the reciprocal. Well, that's because we used the reciprocal of this. We didn't use the proper inverse, we used the reciprocal of the inverse, and so we got the reciprocal of the result we were hoping for. Now, let's take one last quick look here and see if the domain and range of the inverse function line up with the range and domain of the original. So certainly here, we don't want the denominator to be 0, and the way we avoid that is we don't let it be negative 2. So the domain of the inverse is that the input value cannot be negative 2. That corresponds nicely with the fact that the output value of the original function could not be negative 2. Now, as far as the range of this function goes, well, ranges, again, it's always harder to get without looking at a graph, unless you know about transformations. This here is a horizontal shift. And this, as we already saw before, is a vertical distortion. Now we're talking about the range of this. A horizontal shift will affect the x values, not the y's. So that's going to have no effect on the range of the function. The 5 is a vertical distortion, but the same way up here we said the vertical distortion did not affect the asymptote, it was the shift, the vertical shift that affected it. We get the same situation here. This 5 that is a vertical distortion will not affect the horizontal asymptote y equals 0 of the original rational function. So we do have two transformations, but neither of them is going to affect the y-coordinate of the horizontal asymptote of the basic function, which was 0. So y still cannot be 0, which corresponds nicely with the fact that the input value of the original function could not be 0. So the inputs here correspond with the outputs here. And the outputs here correspond with the inputs of the inverse. Always nice when a plan comes together.